Good morning, everyone. Today, I'm going to present our paper, a hierarchical graph-based framework for cross-subject emotion recognition using multimodal physiological signals. The presentation is divided into 5 parts, and let's begin with the introduction. Emotion recognition has become an important topic in intelligent healthcare because our emotions influence cognition, behavior, and mental health. Therefore, an accurate and objective emotion recognition systems has broad applications such as mental health assessment, human-computer interaction, and wearable healthcare. In this work, we focus on physiological signal-based emotion recognition, which provides a more objective way to understand human emotions. Existing physiological emotion recognition methods can be divided into 2 categories. Traditional approaches mainly rely on a single modality such as EEG, ECG, or GSR. However, a single modality provides limited physiological information and is often sensitive to individual variability. Therefore, recent studies have shifted toward multimodal physiological signals, which provide complementary information from different physiological systems and enable more robust emotion recognition. However, multimodal data also introduce new challenges, which motivates our work. Although multimodal emotion recognition has made significant progress, 3 challenges still remain. First, existing method cannot effectively model the relationships among different physiological modalities. Second, subject-dependent evaluation limits their generalization to unseen individuals. Finally, hard labels cannot fully capture the continuous nature of emotions. To address these issues, we propose HGFP, a hierarchical graph-based feature processing framework with soft label learning for robust cross-subject emotion recognition. Next is the dataset. We evaluate our method on the S-certain dataset, a widely used benchmark for multimodal emotion recognition. It contains 2,088 samples collected from 58 participants with synchronized EEG, ECG, GSR, and facial motion signals. Each sample is annotated with continuous arousal valence scores, making this dataset well-suited for evaluating cross-subject emotion recognition. Next, I will introduce our methodologies. Before applying our framework, we first pre-process the multimodal physiological signals. This includes data cleaning, outlier removal, and feature normalization to improve data quality and training stability. We also mapped hard labels into soft labels, which better represent the uncertainty of emotional states. I will explain the idea in more detail later. This figure illustrates the overall workflow of our proposed HGFP framework. It consists of 3 main stages. First, we pre-process the multimodal physiological data and prepare the input features. Second, we apply the hierarchical graph-based feature processing module, where we model both intermodality and intramodality relationships to learn feature importance. Finally, the selected features are used to train an SVR model with soft label learning for cross-subject emotion recognition. In the following slides, I will explain the key components of the framework in more detail. From the 4 physiological modalities, we extract handcrafted features describing brain activity, cardiac activity, skin response, and facial behavior. In total, 223 handcrafted features are obtained and used as the input to our HGFP framework. Our second key idea is soft label learning. Instead of directly assigning binary labels, we map continuous emotion scores into soft labels to better represent the uncertainty of emotional states, especially for samples near the decision boundary. During training, the model learns these continuous targets using an SVR model. Then, an optimal threshold is selected on the validation set and applied to generate the final binary predictions on a test set. This strategy improves the robustness and generalization of cross-subject emotion recognition. Now we introduce the core component of the framework, hierarchical graph-based feature processing, or HGFP. As shown on the left, we first construct a two-level hierarchical graph. At the upper level, handcrafted features within each physiological modalities are aggregated into a unified modality representation. And the Pearson correlation between modality representations is used to construct the modality level graph, capturing the statistical relationships among different physiological modalities. At the lower level, an independent feature graph is constructed for each modality. Each handcrafted feature is treated as a graph node, and feature connections are established based on the Pearson correlation across all samples. A top-case sparsification strategy is then applied to retain only the strongest feature connections, producing sparse and modality feature graphs. After constructing the hierarchical graph, we perform hierarchical importance propagation. First, the initial feature importance is computed using only the training data of the current cross-validation fold. The importance then propagated once within each feature graph to refine the importance of correlated features. Next, the updated feature importance is aggregated into a modality importance score, which is further propagated over the modality level graph to model interaction among different physiological modalities. Finally, the propagated modality importance is fused with the corresponding feature importance to obtain the final importance weight for each handcrafted features. These weights are subsequently used for feature reweighting and feature selection before being fed into the downstream emotion recognition model. Then is the experiment and result. Now let's look at the experimental results. Compared with the existing method, our approach achieved the best overall performance on the ascertain dataset, especially under the more challenging cross-subject evaluation setting. We also conducted application studies, and results show that both feature reweighting and feature selection improve performance, and combining them achieves the best results. Finally, compared with other feature processing strategies, our HGFP framework consistently delivers the highest accuracy and F1 score, demonstrating the effectiveness of the proposed method. Besides achieving strong performance, our framework is also interpretable. As shown on the left, different physiological modalities contribute differently to emotion recognition. For arousal, EEG receives higher feature importance, while for balance, facial motion becomes more important. The feature ranking on the right show the same trend, indicating that HGFP learns meaningful feature representation rather than relying on simple feature fusion. Then let's go to the final conclusion part. To conclude, we propose HGFP, a hierarchical graph-based framework for cross-subject emotion recognition using multimodal physiological signals. By combining hierarchical graph-based feature processing with soft-label learning, our method achieves robust, accurate, and interpretable emotion recognition. In the future, we plan to validate our framework on larger dataset, integrate it with end-to-end deep learning models, and explore real-world wearable healthcare application. That's all for the presentation. Thank you for listening.
Subscribe the channel to get instant updates of our publications.